Hello everyone, Human Hard Drive here, today with another AVR-C tutorial. Today we're going to be talking about the Atmega 328P's serial communication system. So that is these two pins here, right below the reset line. I'm going to break this video series into two bits. The first part we're going to talk about transmission and some of the intricacies with the transmitting lines, and then we're going to talk about, in the second video, receiving and some of the nuances with the receiving communication code. So a little hardware setup for this video. Obviously you're going to need your board here. Done a little cleanup yet again of this board. You're also going to need some means of getting serial communication to your computer. You could use a logic analyzer if you have one. I'm going to be relatively simple and just use a USB serial to USB communicator. This is a TTL 232R 5-volt system with one of these jumpers on the end. So let's go ahead and just hook this up. I've got a male-to-male header here, and I just plug that in here so it sockets very nicely into the breadboard. Now the first thing you're going to want to do when setting this up is you're going to want to make sure all the voltages are the same. So I'm going to hook ground into the ground rail like so, and then I'm going to hook power into power. You should look up what the pinout is, because obviously it might not be the same as my pinout. And then I'm going to hook up the RX, it's TX and RX I think, the RX on this to the TX, which is the third pin on the, third pin, it's right there, third pin down. So it's going to go from TX here to RX here, so transmit to receive. Make sure you don't get that backwards. Sometimes if it doesn't work, your first bet is to switch those around, because it's not very standard sometimes transmit here will mean transmit in, sometimes it'll mean transmit out, sometimes it'll be receive in, receive out. I tested this to know that transmit out, receive in, so that's all how that's hooked up. So with that, let's go ahead and start writing us some code. Okay, so got Atmel Studio open with template file. So let's just go ahead and look at the data sheet. So UART section 19 here. It's actually, let me zoom out a bit, called USART because it gives you both synchronous and asynchronous serial communication. So synchronous meaning you transmit at once or you receive at once, not both, whereas asynchronous you do both. You can have full and half duplex operation. So this video is going to be half duplex. We're just going to talk about transmitting. Next video we're going to talk about just receiving, and it's very easy to just stitch those two pieces of code together very nicely and have it all work. You've got 5, 6, 7, 8, 9-bit data frames. 9's a little weird. I've never actually worked with a system that has a 9-bit data frame, but the option's there. 1 or 2 stop bits, odd or even parity generation, and a bunch of things for receiving. Just reading this off, just reading this off the datasheet, getting it through your head, so you can remember all the things that the Atmega can do. And it's got something called multi-processor communication mode, which we're not going to talk about in this video. We might get to at a later point. We'll see how things go. And double speed asynchronous. You can essentially just double the speed of your transmission or receiving, so that you can actually run it slightly faster than your clock should allow, which is an interesting feature. So as far as setting up serial on this, it's extremely simple to set up. All you really have to do is enable one thing and you're good to go. It's pretty much a cakewalk from there. The trickiest thing is setting up the baud rate, and even setting that up isn't that difficult. So they give you the formulas you need, so we're just going to be dealing with asynchronous normal mode, not asynchronous double speed or synchronous master mode, which I think is used with a multiprocessor communication. Don't know. Just going to be talking about general setup here. So asynchronous you're going to be using pretty much all the time for most of your needs. Asynchronous double speed maybe if you need to squeeze more speed out of your processor, but here just asynchronous normal mode. Now you have a baud rate. That's your bits per second, your communication rate. The processor doesn't accept that. It takes something called a UART, which is the data register which contains the prescaler value, which says this is the speed at which we need to run for a given clock speed, which in our case is going to be 16 megahertz. So this is the formula we're going to calculate that. Now the tricky bit comes, if I scroll down all the way, when putting that number you calculate into the data register. It's a 16-bit data register, not that weird. The weird thing is that the lower byte is a full byte, 7 to 0 bit. The upper byte, however, is just a nibble. It's only 4 bits. So while you can write to the register UBRR0 as a whole, it won't actually work if you do that. You have to split it up into the upper byte and the lower byte. So that is the trickiest thing you have to set up when doing this. So let's just go ahead and set that up. We're going to start with a couple defines. So let's define FCPU, and that's going to be defined to be 16 megahertz. We're going to define the baud rate, and I'm going to set that to 9600 baud, and I'll explain why in just a second. Define BRC, and BRC, this is the baud rate calculate. You can call it whatever you want. This is what I call it, which is FCPU divided by 16 divided by the baud rate minus 1, and then I wrap that all in parentheses, because if I don't, I get a warning for some reason, but I'll keep it all in parentheses. Okay, so 9600 baud. The program I'm going to be using to receive the transmission from the AppMega 328P over the USB serial line is this program called TerraTurb. I'll give a link to the download in the description. And it's a really great program. It does TCP/IP. You can do Telnet and secure shell into a couple things from it, but you can also do serial. And the great thing about this is it's one of the few programs I've seen which, if you go into the setup, you can tweak the data frame, so you can have 7 or 8 bits. You can tweak the parity, and it gives you some weird parities here that we can't control on the AppMega, but the option's still there. And you can even set the stop bits. So it gives you a lot of control in just a serial monitor. So we're just going to set this up with the default. You can tweak it to whatever you want, because it's very easy to tweak. Like I said, it's very easy to tweak the serial setup in this. It's just a matter of changing a couple defines. There's not a lot of thinking you have to do to get it to work. So baud rate, data 8 bits, parity none, and 1 stop bit. So I'm just going to run with that. So let's finish up setting the baud rate. So the upper register is UBRR0H. That's going to be BRC, and we're going to do a right shift on that 8 places. And then UBRR0L, the lower byte, is just going to be BRC. I'm going to hit a space on that so it's nice and clean. So this just gives us the upper 8 bits, and that's going to be shifted into the upper byte, and this gives us the lower 8 bits, and that gets shifted into the lower register. And for some reason this works better than just trying to write it all into the entire 16-bit register. And this works every time. So let's go ahead and set up the transmitter now. So there are 3 control registers for the serial bus here. The control registers A, B, and C. A, we're not going to touch right now, at least. These are just a bunch of flags and a bunch of error flags as well. First one we want to set up is control register B, which has the transmitter enable. So let's just set that up. So that's UCSR0B equals 1 shifted left into TX enable 0. Put an extra thing there. And then C, let's see, the status register, control register C. So asynchronous mode, we're not going to touch. We're just going to leave that 0. Parity mode, so you can have even parity, odd parity. If you don't know what parity is, it's the simplest form of error detection. Do just a Google search for parity bit, because it's going to explain it far better than I can in words without drawing a bunch of things. But yeah, it's just a means of checking how many bits are true, and then saying if it's even, do this, if it's odd, do this. So it's just a very simple form of error checking. So we're not going to touch that. We're going to disable the error bits, or the parity bits. We're just going to stick with 1 stop bit. And the character size is the only thing we really have to set up. So to get an 8-bit, not not letting me highlight. No, never mind. Oh, select tool. There we go. So to get 8-bit, we just have to set UCSZ01 and 00 to be true. So UCSR0C equals 1 shifted left into UCSZ01, or 1 shift left into UCSZ00, and there we go. So that sets up the 8-bit data frame. Oh, excuse me, a little cough. And that's it. That is all you need to do to set up the transmitter. So to demonstrate the transmitter, I'm going to include the delay, util delay. Now, to actually transmit something, there's a register for it, and it's a data register. It's the UDR0. So whenever you write to this register, it's going to be sent out to transmit, and whenever you read from it, it's going to be read from the receiving. So we're just going to be transmitting, so all you have to do is write whatever you want to send out to this register, and it's going to transmit it. And you don't have to do anything else, because once you put data into this register, it automatically starts transmitting. You don't have to tell it to start, you don't have to tell it to stop. Very straightforward. So all we're going to do is say UDR0 equals, and we're just going to transmit the number 8. And then I'm going to put in a delay of 1,000 milliseconds. Compile this, make sure I didn't make any mistakes. And I'm going to open up TerraTerm, bring this over here. And now let's upload this to the board. There you go. 8, 8, 8, 8, 8. So it is transmitting an 8 repeatedly. If I tweak the code, I can make it send an H. Compile that again. Run. And now it's sending an H. So it's very simple to just send out data, and this is just sending 1 byte of data every 1,000 milliseconds. So again, all you've got to do is write stuff to that register, and it handles it automatically all via the hardware. So very simple, very easy to set up. So that's the basics of doing this. Let's do something a little extra. Let's say you want to send more than just a byte at a time. Let's say you wanted to create a queue of things you want to send. So let's write that, because it's going to let us look at a couple extra bits that might be useful to you. So let's include interrupt AVR interrupt.h, and let's add a define. So we're going to create a transmission buffer, and we're going to make that 128 bits. That seems like a good size. Now the way I'm going to do this is with a character array, and I know that's going to irritate some people watching this who have been programming for quite a while, but oh, you could probably do it with pointers and it would be a little more simple. I don't think in terms of pointers anymore. I haven't thought in terms of pointers for quite a while, and character arrays are a better way for me to visualize things, so I'm going to be doing it in terms of character arrays, and they're essentially the same thing. So character serial buffer, and that's going to be tx buffer size. That should be a semicolon. And does that exist? Yes. I'm going to create an unsigned 8-bit integer serial read position. So what I'm doing here is creating a dynamic queuing method. So it's going to have two indexes to this array, two indices to this array. One's going to tell it where to read from next to go into the transmission buffer, and one pointer to say where to write next. And those are going to move through the buffer to say, here's where you're going to read, here's where you're going to read, and they're updated. And this way you can have a fixed size, but you can keep writing over and over and over again. So, little quick algorithm. I'm not going to fully explain it because it's fairly evident from the code. It should be fairly straightforward to follow. I'm going to add two methods, void append serial. I'm going to do this with characters. I know that's going to irritate people for some reason. And then void serial write. And again, a character array. And I'm going to space that because it makes it look nice and neat. Okay. So let's start with the append serial method. So what this is going to do is, what this is going to do is it's going to add a character to the buffer. So serial buffer at serial write position equals, so we're going to write the character C to the write position, and then we're going to increment the write position so it moves through the array, and then if we're at the end of the array, we're just going to move back to the beginning. Okay, now let's set up the interrupt vector. The interrupt vector is called UART tx vect. And this vector, if I scroll through this, because we do have to do a little bit setting, works off this. It's going to say the transmit is complete. So everything that's in the UDR register has been shifted out. So that's what that interrupt is going to signify. And in order to set that, it's this bit right here. It is in UCS. It's in the control register B, and that's TXCIE 0. So if I just scroll back up, so or one shift left into TXCIE 0, and I'm going to space this out again just to make it look nice and neat. Okay, and I'm going to delete this because we're not going to use it. And then I'm going to enable interrupts right here. And so what are we going to do in the vector? Well, what we have to do is if serial read position does not equal the serial write position. If the serial read position and the serial write position are the same, it means we've gone through the entire array, and now these two indexes are at the same point, so we don't have to read anymore. But if they're not equal, that means we still have more data to shift out. So UDR0 equals serial buffer at serial read position. And then we're going to increment the serial read position. And then just like the write position, if the serial read position is greater than or equal to the TX buffer size, if we're at the end of the array, we're at serial read position ++. And so there we go. Now there's one more method we have to set up that we created, and that is void. Oh, page down. Void serial write. And what this is going to do is it's going to take an entire character array like a string, or really any, it's going to be a string. So this is going to let you send messages. Obviously, if you can send anything this way. But the character is just any 8-bit, any 8-bit data type. So serial read position. No, not serial read position. Serial write position. Serial write. Come on, position equals. No, I'm reading the wrong method. 4. There we go. Uint 8. I equals 0, I is less than string length of the array C, I++, and then we're going to append C at I. So we're just adding each character in the array C to the end of the buffer. And then I'm going to add this little thing here, if UCSR0A and one shift left UDRE0, UDR0 equals 0. So what this buffer, or not what this buffer, what this interrupt does is when this interrupt fires every time it's done transmitting. So the second you put data in and it's finished sending out that data, it's going to jump to this interrupt. So there's going to come a time when we've shifted through the entire buffer we've created and there's nothing more to send. This is going to stop. This isn't going to fire anymore. So we can keep writing data to the buffer, but it's not going to keep the interrupt's not going to fire. So we need a way to restart that. So the way we do that is by sending it a null character. So it's just going to shift that out, and then once it's done shifting out to 0, it's just going to go through the buffer again. So this little thing here, this UDRE0, is in status register A, or control register A, not status register A, which is this thing here. Flag indicates if the transmit buffer is ready to receive new data, meaning the buffer is empty. So we check that. If it's empty, we send it a null character 0, and that says, okay, we're going to restart sending everything. So that is that. Let's just compile that, make sure I didn't make any mistakes. And these are just a couple things warning me about using string length, saying that if I don't terminate it properly, it's going to get mad. But that shouldn't be an issue. So basically, whenever you're doing this, you want to end it with a null terminator. That is the one caveat to my creating the serial buffer. I know the serial buffer technique isn't perfect, but it's a pretty good guideline to creating your own. So I'm just going to be using this to send strings. Obviously, if you're going to be using it to send something else, you're going to need to send serial write the length of the array so it knows how many things to read into the buffer, or some clever way of getting around that. But for me, I'm just going to be sending messages because it's more interesting in this video. So hello world, so new line, carriage return, serial write, and I'll put in some funky capitalization. And then we're going to put in a little delay of 1500 milliseconds, and then serial write goodbye. And there we go. Let's compile that. A couple warnings telling me that string length may not be the best thing to do, but again, I'm just doing this with strings, so that's, again, the best way to demonstrate this. Oh, this is still going. So I'm going to try and clear the buffer. Oh, wrong part, wrong thing. Let's upload this. World, goodbye, and if I clear this one more time, and I restart this by unplugging it and then plugging it back in. Hello world, goodbye, and there we go. So we've successfully sent 3 strings of characters from the ATmega328P to the computer over USB to serial by using this string buffer. So that is it for the transmission thing. Again, receiving setup in the next video, and then you can just stitch these two together very handily. Transmitting and receiving, very easy to set up. Again, you just have to enable a few things, and pretty much the hardware takes care of everything else. So that is it for this video. I'm Human Hard Drive. Thanks for watching.